student prime. Spencer? Student prime.
Brother probably did.
Oh, yes, probably right. Alright, we're starting on charges today. A lot of this you've probably seen before. Sort of basic principles of charges, insulators, conductors, how charges respond to one another. And then we'll get into Coulomb's law, which looks a lot like Newton's universal law of gravitation. So some of that we've already done. We'll do some more vectors like we did with the law of gravitation. You'll certainly see that on your exam, either with electric charges, electric forces, or with gravitational forces, multi-dimensional vectors, two-dimensional vectors. And then we'll do fields, which will also be very similar to what we had with gravitational fields. And then we'll do potential as well. Actually, I think that's the next chapter, which we've also already seen with gravitational fields, but we'll do it in a little more depth with electric fields. All right, so first of all, let's see. So we often experience the presence of charges. Where do we see charges often? Where you just experience charges. Some places you experience charges. Okay, right. So we experience static electricity in a lot of different ways. Like, for example, where? On the doorknob, right. So if you're just walking around, and especially on a really dry day, you get sparked a lot more. So you'll notice on certain days you experience these shocks when you touch a metal doorknob a lot more than others. Why on a dry day would you experience this static discharge? Or what is it about the atmosphere on a dry day that makes it different from other days around here? The what? The what? No, on a dry day. Oh yeah, so thunderstorms are a representation of static charges, and we'll talk about that. Actually, I think that's a whole more problem regarding that. But on a dry day, what's different from a normal day? So what? There's moisture in the air, right? And what type of molecule is water? Okay, but it rhymes with molar. It's polar molecule, right? That means that one side of it is, even though it's a neutral molecule, one side is a certain charge and another side is a certain charge. I might describe that in this way, but basically, from one side it looks charged, and from another side it looks charged. And so that way, these polar molecules are able to take away charges. Right? So like you're sitting here and you have a certain amount of charge on you and you're surrounded by water, the water can take these excess charges off of your body. And that's why on dry days you build up this excess charge more than you do on humid days. Alright, so static electricity, touching doorknobs, also, like in your car, like as you slide out of your car. Yeah, Josh?
So like on a humid day, because there's more water in the air, is that why your hair kind of gets frizzy, I guess?
No, I think that's just, I don't think so. No. Maybe
maybe because there's more water, so it's taking...
I don't think so. I don't think that's why. I don't know. I would think it would be the other way around, because it's the charges in your hair that will sort of make it stand up. My hair's standing up. Alright, so touching doorknobs, getting out of your car. Any of y'all have like cloth seats? What happens when you close your door?
Make sure you slide out.
Right, if you slide out, what happens there is as you slide your rear against the seat, it picks up negative charges off the seat, and then you're given an excess of charge, and then when you go to close your door, it'll shock through your finger. So your car seat, only a couple of y'all are married, so you won't know this, but like when you kiss another person, unless you're like kissing your mother or something, like if you're kissing your mother, right? Sometimes you get shocks between you and the other person. That ever happened? No? Okay. It's because you live in Louisiana. It's too humid around here. And what I always remember is when I was in high school, I wasn't kissing Chris Reeds. He was my roommate. I went to a boarding school, and Chris Reeds was my roommate. And it was a boarding school where There's a math and science school, kind of like the one in Louisiana, but one in Mississippi. And I remember one night I was up really late, because that's what we did. Like we stayed up late and we did homework a lot. But Chris, on the other hand, was a very good student, and he would go to bed early, like 10 o'clock every night. But one night I was sitting there doing homework, and I got a little bored, and I looked over, and there was Chris. He was asleep, and so I stood up, and we had sort of old carpet in our building, and I would start doing this. And what do I do when I drag my feet on the carpet? Just like the car seat. Right, I build up charge on my body, so I have this excess of negative charge. And then I would go over to Chris and I put my finger right next to his ear. I wouldn't touch his ear, just like get really close to his ear. What would happen? It's shocking, right? I could even see, I remember, you could even see the little blue spark, because it was a very dry day, and I was able to build up a lot of charge in my body. He didn't wake up, fortunately, because he was kind of bigger than me and stronger and things like that. But he would just sort of twitch. And, so anyway, Chris reads. Maybe if you live in a dorm with a roommate, you can do that. Oh, you don't have roommates on campus much anymore, do you? I have a roommate on campus. Yeah.
Have you ever watched Family Guy?
Family Guy, the cartoon.
Oh, there's so great about that. It's really funny.
I haven't seen that. Okay. Let's see. Dealing with charges works best on dry days. Why? And the reason is, I already said this, because water is a polar molecule. And the water in the atmosphere takes away excess charge. All right. When a material has excess positive or negative charges, it is said to be electrically charged. And actually, in reality, we usually talk about objects not as having excess positive charges, but as having a deficit of negative charges. We'll talk about this in just a second. Why is that? Why do we don't talk about objects transferring positive charges, but we talk about them transferring negative charges. That is, either they'll take on an excess of negative charge, or they'll lose some of their negative charges. Why is it that we don't talk about transfers of positive charges? Huh? Right, they transfer electrons, not protons. We didn't know this for a lot of years, but in recent past we know this, that the protons are very tightly bound in the nuclei, and so they're not transferred very easily. But the electrons, in some atoms at least, are transferred very easily. And so that brings up the difference then between conductors and insulators. But first, some properties of charge. So this is sort of grade school stuff, you should have seen it. You have both positive and negative charges. Positive, of course, are protons, negative are electrons. As Harley said, our positive charges are tightly bound in that nucleus with the neutrons, and negative charges orbit around the nucleus. Our like charges will repel. This will become important when we deal with Coulomb's law. Opposite charges will attract. So for example, if I have two positive charges here, they're going to repel one another. If I have a positive and a negative charge, they will be attracted to one another. Third grade stuff for y'all, right? Heard all this? Yeah. All right, number 4. Charge is conserved, and then charge is quantized. And there is no 6. Alright, for charge is conserved, we talked about this last semester about matter being conserved, mass being conserved. That is that you don't lose mass, or you can't create or destroy matter. The same thing here is that you can't create or destroy charge. that you simply transfer it from one point to another, right? And then charge is quantized. What does it mean to be quantized? What does that word mean? Talk about this in PChem. Okay. What does quantized mean? Comes in particular what? Right, what is it, Hunter? Quantities, right. So to be quantized just means that it comes in very discrete quantities. So like, for example, when we talk about light, we talk about the light comes in quanta, or particular discrete quantities. And similarly for charge, charge is quantized. Charge comes in very discrete quantities. Those quantities are based on the fundamental unit of charge, 1e. I think I have this on the next slide. But 1e is equal to 1.6 times 10 to the minus 19. That's in coulombs, which is the unit for charge. And of course, that's the charge of what? 1.6 times 10 to the minus 19. If you don't know it, it's a good number to know. Like, especially if you're chemists, you should just know that number. What is it? It's the charge of what? It's an electron, or a what? So electrons and what have the same charge? Protons, right. So that's just the charge of an electron or a proton. It's the fundamental unit of charge, and you can't have a half of a proton or a half of an electron. So whenever we're talking about charge being quantized, that means it comes in fundamental units of plus or minus 1e, plus or minus 2e, plus or minus 3e, so, and on and on. So you can have one electron, you can have two electrons, you can have three electrons, but you can't have 3.5 electrons. And so these would be, for example, 1.6 times 10 to the minus 19 coulombs. 2 electrons, or 2 protons, would be 3.2 times 10 to the minus 19. And then 3 protons or electrons would be 4.8 times 10 to the minus 19 coulombs. But you can't have a value in between these values. And that's what it means for charge to be quantized. It comes in particular quantities. Yeah? Yes? All right. And as I said, the fundamental unit of charge is 1.6 times 10 to the minus 19 coulombs. And coulombs is the SI unit for charge. It's named after the scientist. I forget his last name. So it is capitalized when it's abbreviated. Okay, let's try this quick test here. Which of these is not a valid charge? 1.6 times 10 to the minus 19, 5.4 times 10 to the minus 19, negative 3.2 times 10 to the minus 19, or 54 coulombs. Alright, is anybody missing their clicker today? 14. I'm going to stop at 1 minute. Still missing a couple people. 5 seconds. 14. Just a couple more seconds. Alright, let's see. We're sort of all over the board. A lot of you put D. Let me show you what happens if you have D. So D was 54 coulombs, right? So what you want to do here is 54 coulombs an integer number of protons or electrons, in this case protons? So if I divide that, 54 coulombs is equal to 3.375 times 10 to the 20th protons. Is that an integer or a decimal number? It's just a really big integer, right? It is an integer. It's written in scientific notation. It's 3375 with 17 zeros. So it's that number of protons. So that is an allowed value. It's an integer number of protons. It's a really big number, but still an integer value. So the answer then is what? If B is not right, what is the answer? B is right. So this is 1 proton. This is 2 electrons. This is that really big number of protons. And then this is, what's that, like 3 point something protons. And since you can't have a fraction of a proton, this one is not a valid charge. So B is the right answer. All right, we've already talked about this. Objects become charged by transferring what? Electrons, not protons. And why is that? All right, they're really tightly bound. So protons are tightly bound to the nucleus. Early scientists thought that the protons were the ones transferred, and so we'll see when we start dealing with circuits that when we talk about circuits, we often talk about the movement of protons in the circuit, and that's just because scientists like Ben Franklin thought that protons actually moved around and not electrons. But now we know that electrons are the ones that move, not the protons. All right, so insulators and conductors. In conductors, electrons move freely. In response to other charges. So for example, in a conductor, if I bring a charge up next to another charge, that charge will move freely around inside the conductor. So if I bring a positive charge up next to a negative charge, the negative charge will move in the conductor up next to the positive charge. Or vice versa, if I bring a positive charge up next to a positive charge, it'll move away within that conductor. It's just a type of material where charges can move freely. Actually, electrons can move freely. So some examples. What are the prime examples of conductors? Metals. So almost all metals are good conductors. Copper, for example, which is what we use in our home, in modern homes anyway, for wiring our homes. What do they used to use in homes for electrical circuits? Do I know? Like prior to about the 20s or 30s. No, they used aluminum. So aluminum is an okay conductor. Any other metals that are excellent conductors? What's that? Gold is a very excellent conductor. That's why anybody do stereo stuff in their car? Yeah, so what do you use on the terminals?
I don't know, I don't really buy that high quality stuff, but I know my AB and my cable is that gold color.
Yeah. Alright, so gold, what is that, AG? Yeah. So gold is an excellent conductor. In high-end stereo systems, they talk about these gold-plated terminals because you... What's that? Oh, is it AU? What is AG? I don't know. Sorry. Thank you. All right. So most metals are good conductors. Insulators, electrons do not move freely. We say in response to other charges, but really the way that we're going to think about this is they don't move freely in response to an electric field, which we haven't really defined yet, but it's a lot like the gravitational field, except due to electric charges instead of masses. So we'll get into that later in this chapter, what is an electric field. Some examples of insulators, or what? Styrofoam, rubber, what? Huh? Wood is an excellent insulator. Wood, rubber, huh? Plastic, yeah. basically, if you're a good thermal insulator, you're probably a pretty good electrical insulator too. For the same reason, right? Because thermal insulators, or thermal conductors rather, the way they transfer thermal energy is through those free electrons. You'll have a source of heat on one end of the conductor, and it'll excite those electrons, and they'll transfer the heat to the other end. So thermal conductors and electrical conductors are good conductors for the same reason, because those electrons move around freely and can transfer energy more readily. See, let's see. So if one area of a conductor is charged, the charge evenly distributes itself across the entire surface. Alright, so say for example, somehow I take some charges and I put them onto this conducting sphere, and I just put a bunch of negative charges onto it. They're going to move around freely on this conductor, and because of the forces between them, because like charges do what? Attract or repel? They repel one another. They're going to distribute themselves evenly, so that after you put them on there, you're going to get negative charges that are distributed evenly all around the sphere. However, when an insulator becomes charged, almost always the charge stays in place, because they don't move around. They want to move around, but they don't, because on an insulator, charges just don't move around very easily. Now I'll show you in a little bit when we pull out the Van de Graaff generator, how if you have a lot of charge on an object, even if it's an insulator, like me, what am I, a conductor or an insulator? Well, a pretty good insulator. I'm a very high resistance, so it's hard to put electricity through me. So when I put charges on my body, because I'm mostly an insulator, then they should stay put. But if I put a lot of charges on it, then they will sort of distribute themselves on my body. So that's charge on an insulator. We have a couple different ways of charging. We have charging by conduction and then charging by induction. Charging by conduction just requires contact. So say, for example, I have a charged conductor here, a metal rod that has an excess of negative charges, and then I have a neutral conductor here. That means that it has equal numbers of positive and negative charges. If I bring it close, actually here, when I bring our charged conductor up next to my neutral conductor, I get a distribution of charges that looks like this. Because as I bring this charged conductor up here, it causes a distribution of charges that basically causes all my negative charges to chase over here, and then I'm left with a positive excess over here. Let me show you a little thing. So this is a piece of copper wire. Like this came out of our house, so this is the kind of wire that you have in your house. Of course, it doesn't look like this. It has a plastic sheathing over it, and then it's inside a bigger wire with two other pieces of copper wire. We'll talk about household circuits and how they work later in the semester. I think chapter 4 or so. But right now, we just sort of consider this as a conductor, piece of copper, and then this is just a plastic rod. But if I rub this wool sock onto the plastic rod, what will happen to the charge on it? Just, what's that? Right, I'll get negative charge. This is like rubbing my feet on the carpet, and I'll get an excess of charge. It doesn't really matter if it's negative or positive, but we'll say that it's negative. If I rub this on this old nasty sock, it's just not going to fall off. And then if I bring it up close to this rod, I'm going to get an excess of, or I'm not going to get an excess of charge. There's no transfer of charge, but I'll have negative charges here. What will this end be like? This end will be positive, and then this end now will be what? Negative. If I take it away, the charges will distribute themselves evenly again. Now, how should the copper wire, how should it be? Should it be repelled or attracted to this rod? Repelled or attracted? Attracted, right, because just like here, I'm going to have negative charges here and positive charges here. So since opposite charges attract, I should have an attraction between the rod and the negatively charged, the wire and the negatively charged rod. So see, it's not a real strong attraction, but I can make it move around. See that? Alright. So, if I touch the tube, however, my negative charges here will travel on to the conducting sphere, and then I'll get a system initially that looks like this. Alright, and then when I take it away, I will have a net negative charge on the sphere. So that's called charging by conduction. Charging by conduction requires touching of the object. You'll have some multiple choice questions on your exam that just talk about sort of how charges respond. I'm going to show you some example questions later, and you'll see them in the concept test too. But it just basically deals with that idea. What do conductors and insulators do? How do they respond? And then how do positive and negative charges respond to one another? So hopefully that's familiar to you. That should be grade school stuff. Maybe you didn't get into conductors and insulators, but certainly charges you should have seen. Alright, you can also have charging by induction. So say, for example, we have a conductor here that has positive and negative charges. And here I'm going to bring a negatively charged object up close to it. So I have negative charges, but it doesn't touch. And then just like we had before, my negative charges are going to go over here. My positive charges here. And then I can connect it to ground. This is the symbol for ground. Basically, the Earth is a reservoir for charges. And if you ever have any excess of charge, you can connect yourself to the Earth, and that excess charge will go into the Earth. And whenever we talk about ground, that's what it means. So for example, in your house is grounded to the Earth. You go outside around your house by the electric meter, there's a piece of copper wire coming down the wall, especially if your house is newer, sort of post-1950s, and then it's connected to a stake in the ground. You know what I'm talking about? You know, that little thin copper wire coming down from your power meter. That connects it to the ground, and that basically allows a path for all the charges to go into the Earth. And we'll talk about that in a later chapter and what that means. So when I have this, I have my positive charges over here, and then I have my negative charges over here. Because these negative charges move around freely, they're going to all go down into this ground, and then they'll go away. And so when I take everything away, I'm going to have a net positive charge on this sphere. So I have a net positive charge. This is called charging by induction because it doesn't require any touching. I've induced a charge on that object. All right, let's try a little quick test. Okay, so in this figure, a ball is made of a conducting material. It's a conducting, not an insulator, it's a conducting material that is attracted to a positively charged rod. What is the charge of the ball? This is an example of like a multiple choice question you'd have. Something else. All right, about 15 more seconds. Supposed to have 14 students in here today. There we go. All right. So I'll stop at 1 minute. Alright, so a lot of you put B as negative. And it is true that if this ball was negative, then it will be attractive. But you can also have it so that it's neutral. How is that? How can it be neutral and still attractive? It's just like the copper wire. So you can have this induced charge set up where if it's a neutral object, I can get negative charges over here and positive charges over here. Now the net charge is neutral. It has no net charge, but because of the way that the charges are set up on the object, it will appear to the positively charged rod that it's negatively charged. They'll be attracted. And that's just like this. None of the copper wire was never charged in any way. It's just the distribution of charges was affected. So the answer is, where is it? C. Now let's say we change this question and we said instead of a conducting material we have an insulating material. And let's try it again. If I instead have an insulating material, a perfectly insulating material, what is the charge of the ball? Is it positive, negative, negative or neutral, or positive or negative? Alright, stop at say 50 seconds.
Are we still assuming that the ball is being attracted to the positive charge?
Right, yeah. So same scenario, except instead of a conducting material, it's an insulating material. I'll go for 1 minute. Just a few more seconds. Alright, very good. So if it's a conductor, it has to be negatively charged because, if it's an insulator, it has to be negatively charged because you're not going to get a distribution of charges that are separated like we did with the conductor. And let's see, in insulators, let me show you something. So, you might have seen this before. So I can attract objects that are insulators by setting up this sort of induced charge in them. Well, I just have some paper. Paper is a pretty good insulator. And I have a balloon. You ever seen this before? If I rub the old nasty sock on the balloon, it puts an excess of negative charges onto the balloon. So now I have a charged object. Oh, thank you. And then if I bring it down, no, it's not going to do it. Sorry, I'll show you. That'd be better. It's because it's no, it doesn't feel either, but it's all right.
Anybody using can?
Huh?
Anybody using can?
Yeah, I'm not getting anything for it. So I'll show you in just a bit something else. In insulators, the charges in the material don't move. The charges might move along the surface. So for example, when I rub the sock on this, charges within the material don't move around, but I just get an excess of charges on the surface of the material. Insulator. When a charged object is brought near to an insulator, however, the molecules may become polarized. I have a picture on the next page. I'll show you in just a second. Polarized means that the positive and negative sides of the molecule or atom are separated. They have different sides, basically. Can I go down from here? Yeah. All right. So for example, if I have this positive charged object next to an insulator, I can get a situation where molecules within the insulator become polarized so that the negative side is attracted to the positive object. So here our charges aren't actually moving around, it's just the structure of the atoms are shifting. Alright, let's try this quick test, then I'm going to show you the Van de Graaff generator. Consider these two arrangements of insulating materials. Q3 has a negative charge. What is the charge of Q1? These are insulating materials, and these are two separate scenarios. So Q1 relates to Q2 in this way, and Q2 relates to Q3 in this way. And I tell you that Q3 is negative. So I want to know what is the charge of Q1. Q3 is negative. I'll stop at 1 minute. Again, we have a couple people that aren't clicking in. One of your clickers might not be working correctly. Huh?
They're nothing to do with these two derivatives.
I'm sorry?
Like Q.
Oh.
Q.
Yeah. Okay. All right. Yeah, we're on frequency 8A. Okay, well listen, I'm going to send out your clicker questions, sorry, your concentration credits soon, before we get deep into this semester, and you'll be able to tell, make sure I'm getting your points correctly. Let's see, A must be right. So these are pretty simple. If Q3 is negative, that means Q2 must be positive. If Q2 is positive, that means Q1 is positive. So A is the right answer. But you can see some questions like that in a multiple choice part of your exam. Let's look at the Van de Graaff generator. If you want to come to the back, you'll be able to see better, so you can get up if you like. Van de Graaff generator is just, it has a belt through here. Inside the base, there's a brush. So it's like rubbing your feet on the carpet, and this rubber strap goes through and rubs your feet on the carpet, and it picks up negative charges. And then when it comes up here, it deposits those negative charges onto these little metal wires, and then they go on to this metal sphere. See what's up? Let's see. Outside of the brain scan is my ground. And So that's connected to this sphere, which this is an insulator, so charges that come onto this sphere won't travel to the hand. But it's connected, notice, to this, which goes straight to ground. And so charges are going to move very freely from here into the earth, and then they're basically off. I'll turn it on. So the first thing I can get is I can get a spark between two spheres. Now, generally when you have 1 inch of spark, that corresponds with 50,000 volts.